Today at RobTalk, we have an interesting question that we're going to answer, and it's about robots and how we actually control robots via language. Because one of the really interesting things is we can tell a robot what to do, but all the decisions that have to be made in between that are really difficult for the system and the robot. So if we tell a robot to pick up a box, there's a lot of different things that have to happen in between. And that's why we're going to talk about this today, how that happens, and especially also with the new product that RobCo is developing. And for this, I have invited the absolute two specialists from RobCo. Here that's Clemens, and we have Robert here, which I'll introduce in a second. And they're going to tell us how this actually works. So let me briefly introduce, obviously, Clemens. Clemens, we've had him on the show several times. Clemens is the principal engineer at RobCo. He oversees the development of all the amazing robots and the physical AI that's happening. And for Robert, just to give you a short introduction, Robert is a robotics engineer and researcher with deep roots both in academia and in industry, and he holds a PhD in control theory from Örebro University in Sweden, and supervised by Professor Achim Lilienthal, and completed 2 postdoctoral positions, most recently at Danica Krasic Robot Lab in Stockholm as well, which is pretty amazing. And then you spent nearly 6 years at Bosch, also developing the very practical stuff from e-bikes up to, plug-in Bosch production facilities, which is obviously quite intense then from an industry standpoint. And today, obviously, Robert, you're working alongside with Clemens, and you're developing the new product Alfie, which is an industry robot that, is going to be, I think, industry changing. And you're taking responsibility for everything from hardware design and control systems to machine learning, model selection, and data collection. You're one of the rare engineers that actually bridges the full stack from high-level autonomy concepts down to motor currents and actually move the robot. And that's exactly what we're going to talk to about today. So welcome, you both, and nice to have you on RobTalk today.
Thanks. Exciting to be here.
Thanks for having us.
Exactly. So did I miss anything, Robert, that we have to say for the introduction?
Sounds good.
Okay, very good. So let's talk about how this all happens. Like, how does really the physical movement work from a standpoint of language input? Because I think that's going to be the future, right? So what we all wish for is obviously giving a robot a command by voice, like we're doing right now with all the amazing LLMs, and then, how can we do that, and how can a robot, follow our instructions?
Right. So I guess one way to think about it and how it's often framed in the field is as a hierarchy of system, kind of a terminology borrowed from Kahneman's seminal book.
Mm-hmm.
We often talk about system 2, system 1, system 0. Those are, you can basically see as controllers that take in sensory input from the robot sensors, monitoring the environment, and they make decisions, they output commands at different frequency.
Mm-hmm.
So typically system 2 is the slow thinker, which is good about or has the capability to reason about vision and language. Then this gives sort of commands to the underlying system 1, which outputs kind of commands a robot can understand, things like, for example, target positions and orientations of its hands and effectors or joint angles at the higher frequency, typically around something between 50 and 500 hertz, which means 50 to 500 commands per second, which then goes to system 0, which is sort of the low-level real-time control layer, which in the end makes the robot move.
So that's interesting. So we're basically using the system that Daniel Kahneman in his famous book, Thinking Fast, Thinking Slow, has mentioned, and you're using those systems to help the robot understand its environment and then actually move in its environment, right?
Right. So I think it's a bit of a loose analogy.
Okay.
Right now, there's really a zoo of model architectures and they interplay in different ways with each other. Maybe we can talk a little more about this. But roughly, I think it's fair to say that there is a sort of a hierarchy of feedback loops going on, which some of them, especially to the higher level, learned from data. The lower level typically now is based on more classical control.
Okay, so more classical
robotics.
Learned robotics.
Maybe one way to make that analogy is if you learn how to drive a car, then the first thing is you get into the car and the teacher tells you, okay, now put in the first gear.
Yeah.
And so what you do is actually symbolic processing, right? And then you have to somehow come up with a very complicated means to turn these symbols, the words that you hear, into actions.
Mhm.
So this is the whole system 2 thing. And so then what you do is slow, it's clumsy, it takes a lot of energy.
Mhm.
It's probably taking a huge part of your brain as well. It's a big model. And then over time, over the course of the getting the driver's license, the task is then to make that automatic.
Mhm.
And so then we're in system 1 land, and then
Okay.
it becomes like second nature, muscle memory, as you call it.
And does then system 0 mean that would be like, is there anything comparable to a human person to get that analogy right? Or is that like, would it be like a subconscious, or is that already system 1?
Absolutely subconscious. So that's almost like happening in the muscles themselves. It's like when another analogy, when you think about a gym and somebody tells you to move, you don't really have to think about which muscle to
Yeah.
use. It just happens. And so that's
Luckily.
the subconscious part that we don't have to think about.
What is the hardest part of that chain? So when we're talking about system 2, system 1, system 0, what is the hardest part of the chain? The language understanding, the decision making, or the physical control?
So I think all of them are hard. But system 0 is the one that in robotics at least has been researched for decades.
Yeah.
Whereas the other ones have been worked around by algorithms until recently. And now we're entering the stage where these can be learned, and where there's still a lot of research happening, where we still haven't quite figured out everything end to end, but where we already see now that things start to work and start to work really well.
Mm-hmm.
I think one key point to mention here maybe is a challenge is what you could call the physical grounding. So there has been a lot of progress in large models, really understanding vision and language to some extent quite well. But the problem remains how to translate this then into an action representation that a robot kind of understands, right?
Yeah.
So that I would argue is one of the key points, and still which still needs sort of work to really figure this out.
Is that also the biggest challenge of the system 2 learning? So that the system 2 is the translation of language into the robot understanding what to do in the first step, and then translating it into how the processor moves the arm or moves the robot?
I would say that's rather, if you want to use this hierarchical analogy, maybe it's rather placed in the system 1. So system 2, you can imagine maybe as some sort of high-level planner which produces sub-goals. If I tell the robot, I don't know, go and pick up a water glass, what system 2, the high-level planner, would do is sort of implicitly break this down into sub-goals. I don't know, grab the glass, move it over there, put it down there, and output a representation which, depending on how it's implemented, it's not really human understandable. It might be what's called a latent vector, a number of rows in a high dimensional space, which is then passed on to the lower level system, which then the translation to robot action has to happen.
Okay, then maybe to explain to our audience, let's take us through the moment that we tell somebody to tell the robot to pick up this glass, for instance. Where is like what happens in system 2, and where is there like a clear handoff to system 1? Or is it still, I don't know, just maybe you can take us through the process.
I would say it heavily depends on the specific model you're looking at. There are models which have a pretty clear distinction, which might be even semantic kind of goals, sub-goals, like key points on the object, things like that. More typical is that the handover happens via some abstract row of numbers, typically in a high-dimensional space. Other models don't really have this strict explicit separation between system 1 and 2, and rather combine them in one big model. I think it's fair to say it's still an open question what the best or most promising architecture will be. Pretty much now, every month, there are new innovations, new models popping up in research or from startups like ours.
Yeah.
We have to see where it goes, I think.
Yeah. So what we're interested in is always taking the one that at a particular point in time works the best.
Mhm.
So we're kind of looking at metrics and how well they perform, and then we plug in and swap out and try different things. So that's it's a kind of an applied research task, but it's also the one where we are in the position to work with, right?
Mhm.
We have the actual use cases at hand, and so we just try to solve the problem by whatever means.
Mhm.
And I think, as Robert said, the main difference is: do you turn a high level command into language first, or do you turn it into the internal language of the machine?
Yeah.
Meaning these are big vectors and just numbers that nobody really can look at and understand.
Yeah, that's very interesting. We always, I think, right now, if you're looking at how large language models work, we always think about that when we enter language, that it kind of understands what we're saying. But for a robot, obviously, the dimensional space makes it even more difficult to understand. Like, we never said where the glass is, so there's a lot of complexity to this, which is very easy for us humans. You compared it to a toddler in one of our podcasts, where you said, like, it's for a toddler at the beginning, for a baby, it's very hard to understand the physical realm. But then it gets super easy because it's learned, and the brain has such an amazing capacity. And then for a robot, this is much harder in the beginning. And you just said system 2 needs a lot of processing power for this. And then it gets easier and easier because it's learned, and then it tends to get better. And I guess when everybody's using, AI right now, I think people underestimate how difficult a physical realm is to understand compared to just a piece of text, which is also difficult, but which was conquered like 3 years ago from, the LLM producers. And you guys are now on the path of, conquering the physical realm. So that's very, very interesting how that is done and how the complexity is.
Yeah, but I think we are now at the point where we have a chance to solve the problem. Because if you think about robotics 10, 15 years ago, it was algorithms that you could say the mathematical functions, but they all talked their own language. It was really hard to connect them.
Yeah.
For example, how do you connect a language input for which you had language experts dealing with it, finding some representation, to robot movements, which has a completely different representation? So the more you connect these in the neural net sense, the more you can train these things end to end. And so then internally they find their own language. They start communicating random numbers, and then by giving them a constraint to learn and a goal, they suddenly form structures on their own. So that's I think the most fascinating thing that has happened for the general area of computer science in the past 10, 15 years, and in a small community of believers in the 30 years before.
It's fair to say, but I think, kind of as you alluded to before, language is inherently discrete, right? So for each language you pick, there's a finite amount of words which you can use to form expressions. But the physical world, the space of motions, of positions and velocities, inherently continuous. So you can imagine it as an infinite dimensional kind of problem. So
Yes.
it remains challenging in that sense.
Yeah, just as you're mentioning it, if I tell the robot to pick up the glass, for instance, he doesn't know which speed is required: slow speed, safe speed, or super fast speed.
Right.
So there's a lot of, where we as humans, we don't think too much about it. But this all has to be decided by the machine. Is that something that layer 2 would, the system 2 would then decide? Like,
yes, it would decide it. The current paradigm is basically or mainly based on imitation learning. So basically, it needs to be fed with expert demonstrations, which is one big open question right now, is how to get them at the scale that's needed. And what the system would implicitly learn is to mimic these demonstrations, which would also encode things like the speed, for example, in a naive way.
Tell me a bit about Alfie from RobCo. How does that fit in, and what is the idea for this robot, and how does that? Well, what's the plan on using the different systems?
So Alfie is the physical realization of what we had in mind for quite a while, making an AI first robot, starting from having a very useful robot in the industry space. So it is a half humanoid. So we're focusing on the manipulation problem. We're putting eyes there where human eyes would be,
Cool.
simply because this is how you collect the data. But it has all the properties of an industry robot, meaning it's maintainable, it's sturdy, it's made for use 24/7. It has all the properties of the RobCo industry robots that we have. So it brings together the best of both worlds.
Something interesting that you said about Alfie is that it doesn't follow a certain script. It basically is calculating probabilities in real time. So it's not a classic robot. It's more like it's a very dynamic robot. And how does that actually work?
So first of all, it can follow scripts as well, because we have this 5-level ladder of autonomy. So level 3, in that would still combine things with classic, Cartesian programming, if you will. So you can move somewhere, and then you can have a learned policy. We talk about policies soon. To do the last 5 centimeters. But then the other extreme is the topic that we're talking about today, which is everything is end-to-end learned, and so it's all picked up from demonstrations, from being pre-trained with large models that have seen a lot of things in the world, and then hopefully you have to do only a very few demonstrations in order to make it do something really well.
So that means like the basic function, the basic movement is not a policy. It's more like it does it itself, and then but the policy at the end, how to tightly grab the glass, or maybe not to tip it over, would that be defined in a policy, or how does the policy work, and who teaches the policy? Is that a demonstration?
So maybe. Again, an image for that. What is a policy? If you imagine you approach with a car a traffic light, the traffic light is yellow. Now you can do two things: speed up, or slow down, right? Yeah. So these are the two actions that you can do, and given all what you've learned about the world, flows in within a millisecond. So you either, like without really thinking about it a lot, you either press one of the two pedals. And what comes in here is all your experience with how fast am I, how far away am I from the traffic light, and also things like, okay, what's the cost of a ticket if I get caught? These are things. These are all constraints. Also, of course, will I be dead when I do it? These are like the cost functions that have all come in through lots of experience in that single decision. And so, really, input is sensory information, state information, where I am, all the things that I see in my surroundings, and the output is a probability for certain actions.
And well, maybe you can answer this one.
Maybe just a small add-on to what Clemens said. I think the idea of Alfie is, for now, that we can combine sort of best of both worlds. We can choose parts of classical choreographed automation, if you will, and only have sub-problems solved by a learned policy. I guess we envision over time the sort of proportion of what's learned in accomplishing a task will increase, but we don't necessarily right now have to sort of solve everything end to end with a learned policy, which, depending on the use case, and we look at the huge variety of different use cases from sorting, industrial assembly, logistics, it's right now would be very challenging to say we come up with one AI model which can solve it all. So what we will do is we will go step by step and try to sort of introduce these techniques gradually. And Alfie will be for us the platform to do that.
Yeah, but it sounds like a really huge advantage that you don't have to train end to end, because I think that takes a lot of training and is probably very limiting in the amount of time you need to train. but then having specific policies to do something at the end of the movement or at the end of the action very precisely?
It's very use case dependent. We have looked at use cases like laundry sorting, for example. That's where you just hit a wall with classical automation. How would you detect the the position and orientation of a dirty sock and, and do something with it? So there, right now, the only avenue basically is end-to-end learning. However, right now, these models are not perfect, especially when it comes to accuracy and things like that. So for precise positioning maneuvers right now, maybe a classical approach still has advantages.
And who would then teach the last, like the action for folding the laundry, for instance, like when you have a sock? Would that be learned by a human or a guidance, or you showed some amazing tools how to like grippers and stuff like that? Is that the way how you teach it once or several times?
Right now, we follow the paradigm that we start with a large model which has been pre-trained on internet scale data, images, videos, text, and we collect a fairly small amount of demonstrations on the robot on a per use case basis. Could be something like you show the robot 100, 200 times, 2-3 hours of data, and we do what's called fine-tuning in the field. So we adapt this big model, which is basically reasonably good at many tasks, to be really good at this one task. So that's how we do it now. And we also envision that this necessary amount of fine-tuning of of use case specific demonstration data will decrease over time. And we are also working on ways to really streamline this process of gathering this use case data. That's an active work stream we are having right now.
Very interesting. I mean, I think it's everybody's dream that the robot does the laundry and does some more housework. But obviously, first it will solve industry problems. What happens if a policy that is suggested, or maybe the script even points to something that is physically impossible, or maybe even dangerous? How does Alfie react, or how does how does it work?
So everything in the industrial scenario needs to be embedded in a safety envelope. So this is also where classical robotics comes in. We have safety systems in place which you can override, so they give guarantees to override things. And so you can think of it as watchdogs or guardrails that make sure that the robot doesn't freak out.
Okay. Yeah, guardrails is a really cool system. I mean, I learned that working with LLMs, and to be honest, it's the concept which obviously makes sense, but I think it can solve all of these issues that people have with basically a robot or an AI going, off the rails. That's where you have the guardrails. So I find that a really good concept.
Yeah, but it is a good question, and one of the still big open problems, I would argue, in physical AI, which inherently is about a data-driven way of generating robot motion. So opposed to classical system, a priori, there are no guarantees really what this policy will produce. Guardrails, of course, are a sanity check to make sure nothing really bad happens. But there's a lot of work also ongoing now in really making these policies also aware of what's really, for example, safe or unsafe actions by, for example, trying to limit the kinetic energy a certain action would produce. And that's also something we, or the field as large, is looking into now, because safety is, of course, a critical topic when you actually want to deploy the system in the real world.
So when you have these policies, by the way, then we talked a little bit about how the movements are created, but I really want to understand, like, when you have a policy and you have maybe even the free movement, how does that actually work? How is it actually turned into a movement?
Right. So that would allude to the system zero layer we talked about before. We can keep this analogy. Maybe Clemens mentioned before, if you, I don't know, want to move the hand in front of your face, what needs to happen? You need to activate in your muscles such that, for one, like the gravitational force is overcome. You need to produce enough force to actually, hold your arm,
Yeah.
counteract the masses. But you also need to counteract inertia. You have to add additional force to accelerate and decelerate in time the movement. And how humans do it. So I'm not a neuroscientist, so I don't want to lean too far out of the
Yeah.
window, but I think it's fair to say that there is a sort of internal representation of the physics of your body, like how long the lengths of your arms are, how heavy these body parts of yours are. And similar, it's in the system zero in robotics. There is a model of the robot which captures kinematics and dynamics, which is masses, inertia, and so on. And that's used basically to produce motor currents, because motors in this sense would be the analogy to the muscles, and sort of reactively adjust based on the sensors on the robot, in this case joint angle sensors, joint velocity sensors.
Very interesting. And for me, that is something that I see it as the system zero must be like an API where you don't have to program it per se anymore directly, but you can send commands in and then it will be executed. And I think
from the exterior, it's pretty much exactly that. I would argue, and it's in modern system largely based on classical Newtonian physics and math. So this layer typically is deterministic, well understood, has clear guarantees. Although in modern humanoid robotics, the layers, even on system zero, blur. So if you see fancy kung fu videos of humanoids, these have some learned aspects, even really on the very low level, because you cannot arbitrarily move. You have to stabilize the whole system as well.
Okay.
But I mean, one has to say that this has been in development for many decades. And of course, comes from a time when computers were not very powerful. And it needs to run a loop, a feedback loop, thousands of times a second. So these are really, really very fine-tuned, use very limited representations. You can think of the digital twin of a robot as being just a bunch of numbers that represent the extent of the robot and certain physical properties. So it is a real model, a real digital twin, really trimmed down to the basics.
That is exactly what I was thinking about. How does it really translate into the movement, right? I don't think about my movement, but for looking at a classical robot 15 years ago, you had to program every movement 100% in the perfect position, perfect movement, velocity, and everything. I think that is changing so rapidly right now, and that makes it more like a companion that you work with as a robot, and not just a machine that you programmed once and that has to do only that task. And I think that is very, very interesting. I mean, it makes it way more flexible and faster to learn. And I mean, I guess that's what Alfie is about, right? To help in the industry. Another question. You were at Hannover Messe, one of the biggest trade fairs for the industry, or for industry goods overall. There were some questions asked, and we took the top 3 audience questions. And I'm going to ask them to you right now, and you can answer them, and for our audience, because then they will know what was the most asked question at Hannover Messe. Can Alfie move around freely?
Yeah, it will. It will be moving around. That's like when we started Alfie, we thought that we would focus on the manipulation problem itself, being at an assembly line and so on. But since RobCo is in talks with customers all the time, not doing some blue sky development, we have this running pipeline where requests come in. We know roughly what our customers want, and mobility is very high up on the list.
Yeah, very cool. Tell us a bit about how Alfie was received at Hannover Messe. I mean, I heard and I saw some pictures that it was a big hit.
It was. So we presented Alfie to the real world. We had a lot of press coverage. We had a demo running with our prototype, which you could press a button and it would pick up an analog camera, a Polaroid camera, and would take a picture with you.
Cool.
And hand it off to you. And so we could demonstrate as well that you can disturb the movements a little bit, and it would still work. It would self-correct. And so we overall did several hundred demos, and it worked pretty well.
Cool. Now that's my second question. Like, how does Alfie really perceive its surroundings? Because I mean, you said it just interrupting because Alfie was at the booth, was taking a Polaroid picture and then handing it over. But if you'd move into that space, then something would happen. And that's the second biggest question. How does Alfie perceive his surroundings?
Yeah. So Alfie has several sensors. An important part is visual input, of course. So Alfie has a camera in its head, which can perceive regular 2D images like you and me, but also sort of depth data. So with this camera, it can generate sort of a 3D representation of the environment. Additionally, the current version has 2 cameras on its wrist, which are really helpful to see close-up views when manipulating. It has, like classical robots, what's called proprioceptive sensors, which measure basically the configuration of its own body, so joint angles, joint velocities. In the future, we will envision Alfie also to extend its sensor suites, so things like force and tactile sensors, maybe contact microphones will be interesting, I think, in the closer future.
Yeah, I think the point is that obviously we want to keep the robot maintainable. So, for example, these wrist cameras, they pick up a lot of signal that you would otherwise only get from tactile sensors. So they're kind of not comparable with the human, but they give us a lot of information that we would otherwise have to use, artificial skins of some sort, which, the robots are not self-healing. So per se, that's a problem. Cameras are much easier to replace. So as far like we use them as far as it gets.
That's, you always mention that, the self-healing part, but I think we humans we take it as such a natural that we are self-healing, but obviously, like also in industry use, if you have a robot, parts will break, parts will need to be replaced. So it's a very interesting topic.
Yeah, and that's, I think, also why we're having such a hard time using that human analogy, because once you put this image out that something looks similar to a human, you put certain attributes onto it, and the self-healing part is, I think, one of the most important ones. So we have had tons of discussions on whether it should look different, and I think it still can, right? You could still put a head on there and then have several arms, operating a conveyor belt, for example. So don't want to rule that out. We have a modular robot system. We can do that. But for now, the form factor is just the easiest one.
Yeah, let me ask you about the form factor. That was number 3 top question was, does Alfie have a head and where are the sensors located?
So it has a head right now, mostly as a position for cameras. Future, human-robot interaction mode as well. Not the super highest priority. It's not something new. People have been experimenting with human-robot interaction modes also for decades. We just do what is necessary to build an industrial autonomous robot.
Maybe just to add on to that, so the human form factor lends itself well for data collection. If you minimize sort of the embodiment gap between your machine, the robot, and the humans, which, as we discussed before, still right now has to provide some use case specific data, it makes the process just much easier. But I would say it's not to say that the human form factor is per se optimal for a given use case. And I think in the future, when the data that needs to be collected, or the need for data that needs to be collected for specific use cases go down, we will see also robot morphologies evolve, so to speak, to different form factors.
I think the interesting part there is obviously, like, a human can walk quite well, but if you look at how good a dog can walk or a spider can walk, then obviously there's huge advantages for certain terrains that where a different, even wheels can make sense.
I mean, humans evolved to run, swim, climb, but if you just want to move parts in the factory, maybe you just want to roll, right? It would be much more energy efficient, safer and easier.
Yeah, much safer, especially with heavy objects. Something with wheels can be very efficient. Yes. So, what was your funniest moment from Hannover Messe?
Oh, can we say this? And so I have a very clear candidate.
No, the funniest moment is obviously always when there's problems, right?
Yes,
So,
of
so I
course,
think
yes.
out of, let's say 300 demos, 290 went very well. We obviously, for a demo, you only go so far, making it really robust. So
Yeah.
you can't guard for everything. So what we did is we put Alfie in a box so that there's one element which is out of the question. Large changes in lighting, for example. Everybody knows in robotics, lighting can cause issues. Nobody really understands that the human eye is working on a logarithmic level. So here in the studio, we might have 1,000. What is it? Lux?
Oh, I don't know how many looks. It's pretty bright though. Yeah.
Maybe 1,000. If you go outside, even if it's a cloudy day, it's 100,000.
Yeah.
Right. So having sun shining directly on you, everybody knows this from cameras, right? Suddenly you see white, and so this happened to us after 2 days, a cloudy sky. That there was like a time window when a window in the roof just there was bright sunlight and that caused some trouble. Let's say for an hour.
Yeah.
Which happened to be an hour where very prominent
some prominent guests came over and we were
people had to
crouching and
taping umbrellas.
Yes.
We realized that the box is not completely shielded off.
Yeah.
So it was just two what do you say, planes or like sheets of fabric, and so there was some light coming through, and that was in the end, and that together with the door was a problem.
But again, that's something you cannot account for when you're developing it. But once you demo it, you see and you can fix it, and that's the cool part, right?
Yeah, I mean, one thing is that, of course, this is a learning. Not that we didn't know it before, of course. If you go on a customer side, obviously you guard for that.
Yeah,
but
of course.
for a demo, again, there's only so many things that you want to shield for. And so, but just operating the robot for a week, having young guys directly out of university be responsible for that, I think that is just a huge experience.
Cool. What was your most fun part?
Yeah, I would have said the same. Because I happened to be the one scrambling around and taking umbrellas. So for me,
cool.
It was that one.
Very cool. Yeah, closing questions. If you had to sum up in one sentence what the differences or what differentiates Alfie from other concepts in the market, what would you say would that be?
So I think, again, we do this combination of industry, technology, and sturdiness together with the learning aspect from humanoid robotics, and really finding the place where we can take the best of both worlds. This is what we're really striving to achieve.
Very cool. Yeah, Robert.
I would say Alfie is a pragmatic marriage between classic, well-proven technology and modern data-driven approaches, with which we go into first deployments now. We will learn a lot, and I think we are confident that this approach will bring us far in that respect.
Yeah, and that will also, is that the future that you also see for Alfie? Or what is the future that you see for Alfie?
So I think the development will be extremely fast, especially on the model side. I think we had this example of Will Smith eating spaghetti and how it progressed. So I think we will see that in this space too. We have on the hardware side, everything has not changed as much, right? You still build hardware like any other system. So there it's more about, do you have the experience to really bring a product from concept drawings to serious production, where with RobCo we have our share of experience, and so bringing that to the next level. That's where I see, making us have rapid progress.
Yeah, so I also think the most progress will come on the model side. So I
Mhm.
can use this opportunity to sprinkle in one of my favorite topics, which is called world models in the field. So the models we talked about before, learned by imitation, are largely purely reactive. So they are pre-trained, they consume sensor input, and they react to it. But arguably, what we really want are models that understand what effect their actions have on their surroundings and are able to reason, to plan over this. So in the field, that's what's called world models. And there's just right now we see really, I would say, a change in trends towards this kind of models. There's a lot of happening there. And I think they will be a big unlock in the future to achieve real dexterity and also kind of solve the data problem that still plagues robotics to some extent. And for me as a control engineer, that's particularly nice because it ties back to methods from optimal control, which were developed in the space race in the 50s. So where there were kind of, I don't know, satellites and rockets were modeled, how they react under influence of the control actions, and kind of that what brought man to the moon, right? And I think it's kind of beautiful that the circle closes now back, and we see this push in robotics using similar ideas, but on a much bigger scale in this sense.
Yes. I have to say, absolutely beautiful and very nice to close the circle there. But yeah, it's an amazing future. I think the world models will be a pure game changer, as they were for classic LLMs as well. They understand basically the text world, right? And it's a much easier world than the physical world. But the world model then, yeah, what I really appreciate about RobCo, and maybe you can say something about that as well, is how modular you always think. You think in the robots modular, and you also think in the models modular. I think that is one of the huge advantages, that you can create a really big system robot, but you can also create just a small one-arm robot that does something really niche and does that really well. I think that is the huge advantage of using RobCo, and you're never stuck with something because you can always, use the advantages that you are developing at RobCo every day, every week, and plug them into that robot.
Right.
Thank you so much for being here. And if you, obviously, the audience, if you want to learn more, you can always visit RobCo's website. You can also connect with Clemens and Robert on LinkedIn. And we'll put their contact details in the show notes. And obviously, if you like the episode, please like and subscribe and leave a comment here. And send it to somebody else who might be interested in how, the world of robotics is evolving right now. And I can only say thank you very much for listening to these two experts. And well, I hope you'll be here again when it's again Rob Talk, and we're talking about autonomy and the physical AI and the future of robotics. Thank you so much. Take care.